Okay, so like I say, we're gonna do a little bit of review of some Algebra 1 stuff. I think this is some stuff that maybe you didn't probably spend a ton of time with, but you did. And so it's all gonna sort of come back to you. For now, close those things up, or push them down so I get your attention up here. You'll be using those real soon. Let's talk about what this means when we're gonna solve a linear system or a system of linear equations. First of all, what does it mean? What's a system mean in math, you suppose?
Way to do things?
Well, okay, I can see that. We talk about sometimes if you have a system to the way you do something, then you're going to follow some steps. It's a little bit different than that. A system in math means a group of things, more than one of something. So if we have a system of linear equations, it just means more than one. Okay? Let's take these two equations here for a second, and I'm just going to sketch these lines, right? So if we were to look at graphs of these things, let's kind of color code these. This first one, let's make yellow. Oops. What can you tell me about that equation? What would the graph look like? What kind of a shape is that, or what kind of a function? Is it a parabola, or is it what is it? You can tell by looking at it. What form does it match? Slope-intercept. So it's a line, isn't it? Good. So it matches the form, both of these match the form y equals mx plus b. So they're lines, right? Okay, so what can you tell me about the parameters? If I'm going to dial in this line, what are the two things I have to do to get the line that I want? Got to dial in two values. What are the two parameters there? In other words, what's m?
Slope.
Okay, m is the slope. What is it for this line?
2.
2. Okay, so I'm going to dial in a slope of 2, so it's going to make it pretty steep. And we've got a y-intercept of negative 19. Okay, so let's go by like tens here. So that's get it less than that. These are kind of inconvenient lines. Etc. Go by tens. So if I graph this yellow one, I've got a y-intercept of about negative 20, so just a little less than that, negative 19. And I'm going to rise by twice as much as I run. So it's going to look pretty much like that, isn't it? Everybody agree? Okay. So let's kind of review some stuff we talked about prior to Roundup. When we take an equation like this, we take the equation y equals 2x minus 19, and we graph that. The graph of the line is a graph of all of the infinite solutions that make this true, right? We've got an equation here that has two kinds of variables, x's and y's, and so in order to find a solution of this, we have to have values of both variables. I have to have values of x and y that I can plug into this equation that are going to make it true, right? So for example, if I plug in a value of x equals 20, what's y going to be? Well, if x is 20, what's 2 times 20?
40.
40 minus 19? 31.
All right.
So that would give me the point. I go over 20 and I go up 31, and so I didn't draw this very well, but if I had drawn it correctly, that would look like the ordered pair 20, 31, right? Those are values I could plug in that satisfy the equation, that make it true. If I just randomly pick a value, I'm unlikely to get one that's going to be on the line. Like if I pick the value, for example, negative 10, positive 30, that's clearly not on the line, is it? So do you suppose if I plug in 10 for x and 30 for y, it's going to work? No way, it's not going to. It's not going to satisfy the equation, right? This is the locus or the set of all the possible solutions to our equation. Each solution corresponds to a point graphically. So it's like the beads on a string, right? Infinite number of beads on that string. We could do the same thing for this guy right here, right? So this one has a slope of -5, y-intercept of, so roughly that's going to be, I don't know, something like right there, and it's going to go down 1, 2, 3, 4. So it's going to be something like this-ish. I didn't draw it exactly correctly. But once again, this function also has an infinite number of solutions, x and y, right? All the ones that are on that line. For example, in this case, if x equals positive 10, what's y going to equal? So negative 5 times 10 is plus 37. Negative 50 plus 37. Negative 13, right? So we're going to have the point. We're going to have a point here, positive 10, negative 13, for example. Once again, here's a point that doesn't work on that line, right? It's not a solution. Now, when we're solving a system, we're dealing with more than one line at the same time. And so if we're solving a system, we've got to find the values of x and y that work for all the equations in the system, right? We've got to find all the values of x and y that make both of those equations true. What does that correspond to in terms of the graph? We're trying to find the values of x and y that work for both the yellow and the blue lines at the same time. Okay, it's going to be the intersection, isn't it? That one point right there is the only place, that's the only value of x and y that's going to work for both equations. And we can see that in the graph because it's the only point that lies on both lines at the same time. Right? Okay? So our goal then when we're solving a linear system is to find the coordinates of that point. Now there's three things that could happen. We've got an example here where the lines have different slopes. What if the lines, just do a quick what if here, just so we can kind of be prepared for all the circumstances that could happen. What if we've got two lines that have the same slopes? What could happen there? What does that probably look like? They have the same slopes but different y-intercepts. How would you describe those lines? Parallel, yeah. So if we've got a situation like that, where these two lines are parallel to each other, right? Do they ever cross?
No solution.
So there's no solution, right? That's going to be the case where there are no points in common, and so the answer is going to be no. There are no values of x and y that will work. We're going to find this stuff today. We're going to start off focusing on ways we can do this graphically, but then we'll kind of review and maybe review/teach. Maybe you haven't seen all this stuff in this context before. How we could find this using algebra instead of a graph too. Okay. One other possibility. What if the two lines are parallel and they have the same y-intercept? Can you tell me about those lines? So here's the first one. And here's the second one. Yeah, they overlap perfectly. They're the same line. How many points do they intersect at?
All of it.
All of them. Infinite number, right? All of the points on either line are solutions of both, right? Okay, so then our goal is we want to find solutions to the system. We're going to start off doing it graphically. So I'm going to show you two ways. I'm going to show you using technology. We're going to use a lot of technology. And here's a great reason why you're really going to want to have a TI-84, because this kind of stuff is really easy on a TI-84. Let's take an example like this guy. Same example, but we'll solve it using graphing technology. So, okay, so with the calculator, and I'm taping this so you can go back and look at this later if you want to, that's fine. Here's what we do. Okay, where do we go to graph stuff on a calculator?
Something plot.
We go, well, kind of. But to put the equations in, where do we go?
Y equals.
Y equals, yeah. That's going to take us to the screen where we can put in the functions. I'm going to clear those out of there. So I just go down to each row and clear it. I do want to make sure that nothing is highlighted. Like sometimes, this is a real common mistake, sometimes one of those plots will be highlighted, and then when you try to graph this thing, that's usually going to mess you up. Okay, you want to have all those turned off. Okay. All right, so then we're going to go to y1 will make the top one. So that's just going to be 2x minus 19. Okay? Let's just look at that for a second. If I want to graph that, people typically want to just hit the graph button. Okay, that's okay, but sometimes that doesn't work because whatever the window was last left at, that's where we're going to be stuck. In this case, it's fine. But it might be that the window is focusing on some place on the XY plane where we don't want it to. And so a lot of times, instead of hitting graph, the first time you graph something, I'll tell people to go to the zoom menu and hit zoom 6, zoom standard. And that resets the window. This is kind of our, our starting place for the window. This is just the XY plane, right? Sorry. So that's the origin, right? So this is the x-axis and that's the y-axis. Well, we're going, the sort of the normal standard window would be one that goes from x equals negative 10 up to x equals positive 10, and from y equals negative 10 to y equals positive 10. We can change that if we need to, but that's where we'll start. So there's my blue line. Okay, why don't we see the whole thing? Well, because the y-intercept is at negative 19, and the screen only goes down to negative 10. Right? So if we go down further, it would cross the y-axis at negative 19. Okay, let's put the other one in, and we'll resize the window if we need to. Okay, so this one, we got to go back to y equals, and one of the real nice things about the new TI-84CEs is you get different color graphs, which is, it makes it easier to see which one you're working with. So this one's negative 5x plus 37. Now another really common mistake here is to push the minus sign to treat it as a negative. That won't work. It's going to cause an error if you do that. The negative sign is down here under the 3. In parentheses. So we'll go negative 5. And notice how it looks a little different. The negative sign is smaller and it's raised a little bit above the halfway point. So negative 5x plus 37. And then we'll just hit graph because we've already got the window sized. And we lucked out. We can see the intersection here. But if we couldn't see the intersection, all we'd have to do is just make the window bigger, for example, right? Like I could go up here to the window and say, all I need to be able to do is see the intersection on the calculator for the calculator to give me the answer, give me the coordinates of the intersection. So if I'm not seeing it, one thing I could do is just go out and maybe make the minimum and maximum values, instead of 10, make them 100. Okay, and if you do that, the line's going to look pretty much the same. A line is a line, right? Okay, there they are. As long as I can see the intersection, I'm fine. I'm going to go back to zoom standard. Now, I wouldn't have to. But there it is. Okay, now the steps for getting the answer are really simple. So on the graphing calculator, the place that you typically want to go when you want to use the graph to answer a question, you always go to the calculate screen, which is second, and then right there, F4. See the blue calc up there? Second calc. And it gives me a list of all these things I can do for the function. And these are all useful, and we'll talk about many of them, not all of them in this class. Some of these are calculus things, but which one do you suppose we want? If we want to find where the lines cross, which option do you think we're going to choose? Which one? Intersect, yeah, so 5. So I can either move the cursor down to that row, or I can just type a 5. Okay, and that takes us to the intersect feature. So what's this doing here now? Let me make this a little bigger so you guys can see what's going on. Come on, what's that doing? There we go. Okay, so what's it asking for here? It's prompting me whenever it puts the calculator says something with a question mark. It's wanting to know, is it correct? Is this the first curve? Y1, which for the color ones is the blue one, which makes it easy. If you're not sure, you can always move the cursor and it'll walk along that line. So if I go like this to the right, my x value will increase, and pretty soon here I'll be able to actually see the cursor on, just think of it like an ant walking on the curve. There it is. Well, that's the one I want, right? That's the first one. So I just hit enter to say yes. That's the first line that I'm interested in finding an intersection for. So is the second one this guy? Is it Y2? Well, if I move along, yeah, now that ant's walking on the red curve. So yes, it is. Hit enter. Now it wants a guess. Now for some functions, this is important. When it asks for a guess, it wants me to put the cursor close to the actual intersection before I hit enter. For lines, it makes no difference. There's only one intersection, if there are any, right? Or there's infinite, in which case, it's obvious. And so I don't even need to move the thing. I can just automatically hit enter. And it thinks about it for a second, and it gives me the intersection. So it's telling me, look at the bottom, that's like an ordered pair, isn't it? X, comma, Y. So that's effectively telling me that the intersection is at this point right here, which has coordinates. Maybe I can't write on the... Yeah, maybe I can't. Well, if I do this again, I bet. Yeah, there we go. So it's at 8, -3. Those are the coordinates of that place. Make sense? Okay. So once again, if we go back, we can make this pretty quick. I mean, you'll be able to do this in just a few seconds once you kind of get used to it. All we're really doing is, if I've got them back at graph, if I want to find the intersection, remember I go second calc 5, right? Second calc 5 gets me to intersect. And then if I've only got 2 lines graphed, I just hit enter 3 times, or triple enter. Enter, enter, enter. There it is. Okay, no big deal. All right, so that's one way to do it, is using the graphing calculator. There's another way to do this too. Actually, let me show you one more example on the graphing calculator. Let me do one. Yeah, let's try one like this. Okay, so what about something like that? Okay, what's inconvenient about this one is that these lines are not in slope-intercept form, right? They're in standard form, okay? Think about the steps that you would go through to isolate y in each of those equations, because that's all you have to do to put this thing into slope-intercept form, is isolate y. So in the top equation, what are the 2 steps in order to get y by itself? Okay, you'd add 3x to the other side, good, and then
Divide by 2.
divide the whole thing by -2, right? Okay, so I call this solving into the calculator. So all we got to do here then is, let's, on this line right here, we're just going to isolate y into the calculator. So now we're going to do this 2 ways. First way is just not using any kind of fancy fraction templates or anything. If we're just going to put this in, as a, like using parentheses and division signs and all that stuff. If I want to divide the whole part of a numerator by something, how do I do that on a calculator? Like you told me I'm going to add 3x to both sides. So that's going to give me 6 plus 3x, right? I want to divide the whole 6 plus 3x by -2. What do I need to include then? If I just write it like this, tell me what's wrong with this. If in the calculator I try to write it as if I try to write it as something like, oh, here we go. If I try to write it as, what was on the other side already? Do you remember what that number was? Can't see it.
-2 equals 6.
Negative, it was -2, and pretend it's -2 on the other side. I added 3x, and then I divided by 6, is that what it was?
No, the 6 where the 2 is right now.
Oh, I got you, okay, got you. Let me do this, we gotta see it. Six. There, that's better. Okay, so we've got 6 plus 3x divided by -2. What's wrong with that? If I wrote that out as a fraction bar, what would it really mean? What am I dividing by -2? I'm not including the 6, am I? That's equal to 6 plus 3 times x over -2. That's not what I want. How could I fix it? What should I have probably included in that first equation, or that first expression? How could I make it mean not that, but mean 6 plus 3x all divided by -2? What would I have to add? Parentheses. There we go. Okay, if I had added parentheses right there, it would have been fine, wouldn't it? Right? So the moral of the story is when I'm solving something into the calculator, I want to start by opening up a set of parentheses for the numerator. So I can divide the whole numerator by -2 in this case. Right? Okay. Oops. Okay, so we would just do this, right? We would open up a set of parentheses, and we start with what's already there. Well, there's already a 6 there. You told me I'm going to add this 3x to the other side, so I go plus 3x, close the parentheses, and divide the whole thing by whatever's in front of the y, which is a -2. Okay, make sense? If I graph that, it's going to be fine. So if I go zoom 6, there's the line. Did I need to, maybe it bothers you that we didn't clean that up. We just kind of left it as, doesn't matter. The calculator's smart. You don't have to simplify the equation. It's going to be able to do it properly as long as it's correct. You don't need to simplify it, right? So let's do the other one down here. If I want to solve for y in the other equation, what are the 2 steps in order?
We got to add,
So I got to get that y that I'm pointing at by itself.
take away -8x.
Okay, subtract 8x, and then what?
Divide by 7.
Divide by 7. Okay, good. So I'll show you maybe a little different way to do this. Now, if you don't want to use the parentheses, you can also use the fraction template. You can get to that. If you hit the math menu, it takes you into all these different menus of things. There's a math menu, a number menu, complex numbers, probability, and then clear over on the right, there's a fraction menu. So if I hit the left arrow to go over to the right edge, these are all the different ways I can have fractions. Well, we want the top one, numerator divided by denominator. Okay, so that's the one we want. There's an easier way to get to that, though. I could also just get to that by going, yeah, exactly, good. I can also get to it. How do I get out of here? If I quit, let's go y equals... Good, I can just hit the alpha button. This is a shortcut. Alpha F1 takes me to the fraction menu. Notice if I hit alpha, I get these really quick menus here. I get fraction, function, matrix, and y variable. We'll use fraction and y variable a lot. Those are the 2. So we'll use alpha F1 and alpha F4. So then I can either type 1 or just hit enter, and I get this little fraction template. And then what do I want on top? Well, you told me I'm starting off with a -6, right? I'm subtracting 8x, so minus 8x all divided by 7. So I just go to the denominator and put a 7 in, okay? And then let's go graph. And so I can see the intersection. So now real quick, what are the steps to get the solution then? I go second calc. Which one? intersect. So second calc 5, enter, enter, enter. There it is. -6, +6 is the solution. Okay? Make sense? Okay, so we can use the graphing calculator to do all that stuff. You can also, and you're going to like this, you can also use Desmos. And you can do this on your calculators, your phones. You can do it on the computers. I've embedded in all these questions, I've actually embedded a Desmos calculator. So if you hit the open calculator, it just opens up a window with Desmos. The nice thing about Desmos, have you guys used Desmos before? Some people have, some haven't. Okay, it's really easy to use. When you're using Desmos, what's nice is you don't have to solve for y. Like I can just type in this first line just the way it is. I can just go -3x minus 2y equals 6. There's the line. How about that? So then I'll hit enter, go down to the next line, I'll put in the other one. 8x plus 7y equals -6. There it is. So there's the graph on Desmos. How do you think I find the point of intersection? I just click on it. There it is. Okay? No big deal, right? Yeah, not a big deal. Okay, so let's try, just throw a couple more at you here with this. So how about, how about one like that? So I'll just go into Desmos, and I'll just clear those out. I think I can just do that too. I can just hit the arrow, or hit the X and it deletes them. So top one, 27x plus 30y equals 570. So there it is, clear up there. Okay, now I don't see that very well. So on Desmos, it's really easy to find it. All I've got to do is I can drag the XY plane around if I want to make things a little bit bigger. Or I want to zoom out, I can just zoom out like that. Right? No big deal. Okay, let's go down to the next line, and let's do the other one. 9x plus 10y equals 285. Okay, what do you notice about those two lines?
Parallel.
They seem to be parallel. Do we know that they're parallel? I mean, maybe you're thinking, okay, maybe the slopes are just really close. I could find out, though. If I just keep zooming out, they stay parallel, don't they? They never cross. And eventually, it just looks like one line. Right? So we know they're parallel, don't we? Okay? Make sense? Okay? One more. Okay, how about one like that? So once again, we'll go into Desmos. You guys able to get this on your phones too, Desmos? Everybody, try it on your phones once, because on different phones it works differently, and you'll want to do this a lot. I mean, this is a pretty handy thing to have. If you get the option to download the app on your phone, go ahead and do that. I think it makes it easier. Negative 10x plus 6y equals negative 42. Does it look the same? Good. Yeah, it should. You want it to look the same as it, because otherwise sometimes you get if you go to the website, you might get the mobile version, and I don't think it's as good. What happened? What happened to those lines? Yeah, how could I tell? I can turn them on and off by clicking on this thing. So if I turn this one off, it looks purple, right? If I turn this one off, it's right behind it. So they're the same line. Make sense?
Got it.
Okay. All right, so that's our graphical method for finding or solving a linear system by finding intersections, right? Okay, let's take a look at some other ways to do this. How about if let's take this one. How can we do this algebraically? Okay, there's two methods that you probably talked about in the past for solving linear systems with algebra instead of graphing. Okay? What's one? Remember? We have two ways we can do this. So we're solving linear systems. Remember? To get you started. Substitution's one of them. Remember that?
Elimination.
And elimination. There you go. Okay, almost always, they're both going to be feasible, but sometimes it's easier to do one versus the other. And really, oftentimes, you can use substitution sometimes, you can use elimination pretty much all the time. When it's easy to use substitution is if a variable is isolated or it's easy to isolate a variable. So are there, like in this case here, are there any variables that are isolated by themselves?
What?
The y's are, right. The y's are, aren't they? So this is tailor-made for doing a substitution equation because I've got y equals 2x minus 19, and I've got that y already isolated. That means I can take the expression 2x minus 19 and plug that in for y in the other equation, right? And what's that give me if I do that? Well, then I end up getting 2x minus 19 equals negative 5x plus 37. Okay, do you see the advantage of that? The advantage is that now, how many variables do I have in this equation? How many different kinds of variables? One. We eliminated a variable by making that substitution, didn't we? If I have two equations, two variables, then I need to have at least as many equations as I have variables to solve the system. So if we have two variables, x and y, I need to have two equations, right? But we can whittle that down to a single equation with only one variable, which is easy, by just making the substitution, right? And this is, you guys have had tons of practice with this. What would I do here? Yeah, so add 5x to both sides, right? So that's going to give me 7x minus 19 equals 37. Add 19, divide by 7, right? And I get 7x equals, what's it be, 56? If I divide by 7, what do I get? 8. X equals 8. And now what would I do? I'm halfway there. I've got the x coordinate. Where would I go to find the y coordinate? Yeah, plug it back into, in this case, I can use either one of these, right? But what if there'll be some situations where maybe only one variable is isolated in one of the equations. Then you just go back to the substitution equation. So we'll go back to either one of these. How about the top one? If I plug in that x value, I can find y, right? So y equals 2 times 8 minus 19. That's 16 minus 19, which is what? Negative 3. Okay? And so then I have the ordered pair, 8, negative 3 is my answer. Right? Okay? So let's try another one. Okay, that's substitution. Oh. What happened? Oh, I must have deleted. Oh.
you do fractions on Desmos?
How do you do fractions? Good question. How do you do fractions on Desmos? Let's pull up. So what if we wanted to do like y equals 2/3 x plus 7? You just do this. You just go y equals 2. If I do 2 divided by 3, it makes a fraction out of it. And then I just hit the right arrow to leave the fraction. Does that make sense? X plus 7, something like that. Okay? Here's another piece of advice. Like when you're doing fractions on any calculator, no matter how simple the calculator is, if you just put the fraction in parentheses, then you can just treat it like a number, right? It just would be like any other number, and the calculator will see it that way too. Okay? All right, let's try... one of these. How about... Okay, so in that one, you're going to get a few questions like this that are just kind of getting you set up to do substitution. So which of those equations has an isolated variable? Okay, look at that example up there for a second, please. Which of those equations has an isolated variable? Top one. So equation 1, what is the isolated variable? X, right? Make sense? Okay, what if we take one like... okay. Okay, we've got something like this. Are there any variables there that are isolated or easy to isolate? And you might look really hard, but no. The answer is no. How come? Right. I mean, if I wanted to, like, let's say I wanted to use substitution here, it wouldn't be a good idea. I mean, any one of these variables I pick, let's just say I pick that y. If I solve for y, if I isolate it, I'm going to get negative 11 minus 3x. I'm going to get fractions, right? I don't want to be dealing with substituting fractions into the other equation, right? So that would be a bad idea. Now, what if I had one instead like this? What if I had the equation 3x minus y equals 7 and 2x plus 5y equals 10 or something? Is there a variable there that I could isolate easily? None of them are already isolated, but which one could I isolate easily? That one, that one, that one, or that one? 1, 2, 3, or 4? Which one? Which one could I get by itself really easily?
The y.
The y right there, couldn't I? Right? I could get that one by itself because it doesn't have the coefficient's negative 1. If the coefficient is 1 or negative 1, it's really easy to get by itself. What I would do here is I would just push the y over to that side by adding it to the other side and then subtract the 7 back to this side, right? So that's just going to give me, on one side I've got 3x minus 7, on the other side I've got y. So I'd write it like this to get the y by itself on the left. Y equals 3x minus 7, and I would tell you, always put a box around that. That's my substitution equation. Then I'm going to substitute that into the other equation right there, right? Down here I'd get 2x plus 5 times the quantity 3x minus 7, right? Equals 10, and then you can solve that. Okay, are we about done? When are we out of here? Oh, 1 minute, okay. Well, that's good. All right. That'll get us going. We'll wrap this up tomorrow, and then you guys can work on this stuff. Go ahead and plug in your Chromebooks, please.